So now using our spring mass damper example that we just took a look at as motivation, we're going to take a look at this activity and work through identifying the value of the controller gains that make the closed loop system stable. So you can already kind of take a look that, for example, in this case, the open loop system has a pole at s is equal to 1 and s is equal to 0. That s is equal to 1 is going to make that open loop plant unstable. And so the role of the feedback here is to stabilize the closed loop system. And so in this first case, this is an example of proportional feedback with a single gain to tune. In the second case, the controller here is a proportional integral controller, and you have 2 gains to tune. And so your goal is to put these systems, compute the closed loop transfer function, then use the Routh criterion and the Routh table in order to determine the constraints on these gains in order to guarantee closed loop stability. Go ahead and give this a try, and then I'll go through my solution. Okay, for this first example, we have proportional control, which means that this K is simply just a constant representing proportional control, and then this is the open loop plant G. And so this is simple unit feedback, and so we know that the closed loop transfer function that relates Y to R is going to be given by GK over 1 plus GK. All right, and so this comes directly from this setup. We're going to see a lot of this setup, but at the same time, don't just automatically write this down until you check that it matches that setup. So if we go ahead and write this out, you're going to put GK, so the S plus 1, S minus 1, S plus 6, that's all G, and K is simply just the constant now K. So that's just a value now, not a whole transfer function. And then 1 plus that same value. So that's our closed loop transfer function. Let's go ahead and simplify it. We're going to multiply top and bottom by this denominator. And so that leaves me with that same denominator, that characteristic equation of the open loop system. And then you're going to have this term left over from the numerator, and that same term up in the numerator here. If we go ahead and expand this cubic out and then add in these terms, we now get this closed loop transfer function. And so that is the one that we want to analyze closed loop stability. So again, we can use our necessary conditions. So that's a constant, and that's positive, so that's fine so far. We need K minus 6 to be positive, which means that K has to be bigger than 6. And then we need K to be bigger than 0 for the last term to be positive. So now we're going to take a look. Now that this isn't just a simple second order system, our Routh table is going to give us a little bit more information. So I've put down the term for the cubic term, the linear term, the quadratic, and the constant term. Now we compute the Routh table. We're going to take this product minus this product divided by 5, and that gives me this entry. And then this term is going to collect these zeros that are here, so that's going to become a 0. And then to calculate this one more time, you're going to compute based on this block. You're going to compute now the entry K. And so this tells us 2 things. So this tells us that K has to be greater than 0. We already kind of knew that from here. So that gives us that. And then we also know that this whole term has to be greater than 0. And that gives us this term. And when we just kind of combine terms and separate that out, that tells us that K has to be greater than 7.5. And so since K greater than 7.5 is more restrictive than K is greater than 0, this is our complete specification for how we can choose K in order to guarantee closed loop stability. In the second part of this activity, we have a proportional integral controller, and so that introduces this 1 over s term due to the integral part of the controller. So again, when we compute, this is simple unit feedback. So when we compute y, the transfer function, it's just going to be gk over 1 plus gk times r. So if you're noting some patterns here, that's good. That's the whole idea, is to work these examples enough to really understand the patterns and how we go through manipulating these whole activities. So this one's a little bit nasty, but once we put, this is k and this is g and this is 1 plus k and g, once we put those together and we multiply them out and we clear the denominators, so we multiply top and bottom by essentially it'll be a s, it'll also be this s plus 1 and s plus 2 squared. Ultimately, you're going to get a transfer function where the denominator looks like this. So I'm going to leave out a little bit of the math in between. I'll let you work that out. But your denominator should come out like this. So again, that's 1, that's positive. We need k plus 2 to be positive, so k has to be greater than minus 2. And then ki appears as the constant term, and so ki has to be greater than 0. So now we're going to go ahead and plug that into, again, Routh stability. So we're going to put down our terms, again, the cubic, the linear, the quadratic, and the constant. We'll do this product minus this product divided by this to get this term. And then likewise, we're going to use this term, essentially this product minus this product divided by this, which just gives you this ki term down here. And so now all of these elements in this first column have to be positive. That's true when ki is greater than 0, so that hasn't changed. But then now we get ki. If we solve for this, ki and k are going to obey this kind of combined relationship. So now what you'll notice is that k, how we pick k, is going to be dependent on how we pick ki. So we may pick this to be some value that's positive, but then that provides a constraint on how we pick k. And so now this is a kind of a picking these two things aren't entirely independent. And that's important because if you want to maintain stability, you need to pay attention to this, which is a kind of a static relationship, but then this will change as you change ki. So that's how you would use Routh table after you've formed the closed loop transfer function to determine closed loop stability.